In the last video, we explored data processing method for reducing noise in the Raman spectrum. The algorithm we discussed were all based on convolution, essentially a moving window applied to the spectrum. This video introduces a different approach. In Raman imaging, we measure an array of points on the sample. Each pixel in this array corresponds to a full Raman spectrum. By assigning colors to each pixel based on specific spectral features such as peak height, peak position, or other multivariate methods, we can visualize the spatial distribution of the chemical information across the sample. This approach also opens new possibilities for spectrum data processing. Improved quality of individual spectrum can again enhance the quality of Raman imaging. When we deal with an array of measurement points, the Raman spectra within the array often show a certain degree of correlation. For instance, the spectra obtained from one region might be nearly identical. Imagine a dataset where all spectra fall into just 3 distinct groups, corresponding to substances A, B, and C. In the ideal scenario, each spectrum in this array can be expressed as a combination of these 3 fundamental spectra with specific factors. To process such data, we can use a method known as singular value decomposition, or SVD for short. I have no intention of making this into a lecture of linear algebra. In short, the idea is that instead of dealing with 10,000 individual spectra, we identify 3 representative spectra, and every pixel in this array can be reconstructed just using these 3 components. In reality, however, we must contend with random noise. To achieve a perfect reconstruction of every spectrum, we need much more factors, since noise is unique on each spectrum. The primary factors of SVD, those representing the major spectral components, are much larger, while the remaining factors, dominated by the noise, are relatively small. By reconstructing each spectrum using the most significant factors and setting the smaller, noise-related factors to 0, we preserve the most meaningful features while minimizing the random noise introduced by the detector. This method not only improves the signal-to-noise ratio, but also ensures that the reconstructed spectra retain the most important spectral information in the Raman image, making it a powerful tool improving Raman spectra and imaging quality. Thank you for watching, and see you next time.